Welcome to the Department of Mathematics. In last lecture, we have seen De Mor's theorem and its proof and examples on De Mor's theorem. In this lecture, we will learn the applications of De Mor's theorem. Now, applications of De Mor's theorem. There are two applications. First application, nth roots of unity, and second application, expansion of trigonometric functions. Now, the roots of a complex number. First application, roots of a complex number, that is nth roots of unity. Using De Mor's theorem, one can obtain all nth roots of any complex number. Okay. Now question asked in this article, question number 3, prove that nth roots of unity is in the formula zk equal to the cos of 2k phi upon n plus I sin 2k phi upon n, where k denotes 0, 1, 2, 3, 4, 5, dash dash n minus 1. This is the formula for finding the nth roots of a complex number. Okay. So we have to prove this type formula also, and hence also show that the roots are in geometric progression. The roots of nth roots of unity are in geometric progression and their sum is 0. So these articles we have to prove. So question is that prove that the nth root of unity is in the form zk equal to the cos of 2k phi upon n plus I sin of 2k phi upon n, and where k equal to the 0, 1, 2, 3 n minus 1. Okay, and hence show that the roots are in geometric progression and their sum is 0. Okay, now proof. Now here let denote the nth roots of unity, means root n, means 1 raised to 1 by n is equal to complex number z. Okay, let 1 raised to 1 by n equal to the z, where z is a complex number. And then we take the n power to the both sides, then this equation becomes z raised to n equal to 1, where z is the nth roots of unity. Okay, now z is a complex number. Let z equal to x plus iy. Okay, where I is value I equal to root minus 1. So this is a complex number. Now we can write this complex number in the form of polar. So we know that the polar form of a complex number, z equal to bracket r into bracket cos theta plus I sin theta. Now where r is r polar coordinate, r equal to root x square plus y square, and theta another polar coordinate equal to the tan inverse y by x. Now here the given equation is the nth roots of unity, means 1 raised to 1 by n equal to z. So 1 raised to 1 by n, so n is any integer, and therefore 1 raised to 1 by n for any integer, its value is 1, and therefore z equal to 1, where z is a complex number and its value is denoted, its value is x plus iy, and therefore z equal to x plus iy equal to 1, and therefore comparing the real and imaginary part, and therefore the value of x is equal to 1 and value of y is equal to 0. Okay, so these values here we put here and we find the value of a polar coordinates r and theta, and therefore here x value is 1, x equal to 1 here. So 1 square is 1 plus 0 square is 0. So r equal to root 1 plus 0 is equal to the root 1, and therefore root 1 is 1, and therefore the value of r is equal to 1. Okay. Now here the above polar form of a complex numbers, we put r equal to 1 in this, and therefore z equal to the r into 1 into bracket cos theta plus I sin theta, and therefore here then the z raised to n equal to 1. Okay, so nth roots of unity, z raised to n, we get the equation taking n power to the both sides, and therefore z raised to n minus 1 equal to 0. Therefore n, z has a n roots, and therefore z raised to n equal to 1. Now z is cos theta plus I sin theta, implies that, and therefore raised to power cos theta plus I sin theta bracket raised to n is equal to 1. Now by using De Mor's theorem here, and therefore is equal to the implies cos of n theta plus I sin of n theta is equal to 1 by De Mor's theorem. Okay. Now this is a complex number and is equal to the 1 plus I into 0, and therefore comparing the real and imaginary part to the both sides. This implies that the real part cos of n theta is equal to the real part 1, and imaginary part sin of n theta is equal to 0. Okay. Now we find the angle, the n theta, the cosine value of theta, the angle theta is equal to 1, and therefore the angle theta lies between the even numbers of pi, and therefore the even numbers of pi, the value of a cosine is 1, and therefore this implies that the angle n theta is equal to the even numbers of pi, and therefore 2 pi k, k's value 0, 1, 2, 3 up to the n minus 1, and therefore when k equal to 0, so the angle is 0, so n theta equal to 0, so 0 is a even number, and therefore for that value cosine value is 1. Now k equal to 1, so we put here, therefore 2 pi. So 2 pi is even number, and therefore cosine value of 2 pi is 1. Again, k equal to 4 pi. 4 pi is even, so cosine value is 1. And therefore, any even pi of that cosine function is 1. And sine function for even numbers of pi is equal to 0. And therefore, the angle n theta equal to 2 pi k, and where k equal to the 0, 1, 2, 3, 4, 5 dash n minus 1. So n values, uh, that values the condition satisfied. Means cosine value 1 and sine value 0. And therefore the angle is n theta equal to 2 pi k. And therefore theta equal to the, this implies equal to the 2 pi k upon n, where k equal to same value 0, 1, 2, 3, 4, 5 dash n minus 1. Now the putting the values of theta in the above equation, and therefore z equal to the cos of 2k pi upon n plus I sin 2k pi upon n. Okay. So there are k values where k equal to the 0, 1, 2, 3 up to the n minus 1. And also the equation z raised to n power, so the z has a n roots, and therefore we denote the n values of z in the form of k, and therefore n distinct values of z which are nth roots of unity, and therefore we can write the zk, means there are n roots and k is equal to the 0, 1, 2, 3 up to the n minus 1. So this is the n values. Okay, and formula is zk equal to the cos of 2k pi upon n plus I sin 2k pi upon n, equation 1, and where k equal to the 0, 1, 2, 3, 4, 5 dash dash n minus 1. So this is the nth roots of complex number formula. Okay. Now in equation 1 gives the formula for finding the nth roots of unity. Now we find n distinct roots of unity such as for each values of k, we find now from equation 1 for k equal to 0 we put this, and therefore z naught equal to the cos of 0, k equal to 0, so all the values 0, so cos of 0 plus I sin of 0, and therefore cos of 0, 0 is even number, so cosine function is 1 and sine function is 0, so 1 plus 0 is equal to 1, and therefore first roots z naught equal to 1. Now we put k equal to 1 in equation 1, and therefore from 1 k equal to 1, therefore z1 equal to the cos of 2 pi upon n, so k equal to 1, and therefore plus I sin 2 pi upon n. Okay, so this is the second root of the nth roots of unity. Now we put k equal to 2 in equation 1, and therefore z2 equal to the 2k phi. So k is 2, so 2 into 2 4, 4 pi upon n. So cos of 4 pi upon n plus I sin 4 pi upon n. So this is the third roots of unity. Now we put k equal to 3 in equation 1, and therefore z3 equal to the cos of 2k, k value 3, so 2 into 3 into 5, so 6 pi upon n plus I sin 6 pi upon n. So this is the fourth roots of unity, and in this way we find n roots and so on. Now last we put k equal to n minus 1 now from equation 1, and therefore z n minus 1 is equal to the cos of 2 into n minus 1 into pi upon n plus I sin 2 into n minus 1 pi upon n. So this is the nth roots. Okay. Hence, the n distinct roots of unity z raised to n minus 1 is equal to 0 are first root z naught, we denote here z naught, then z1, z2, zn minus 1. So these are the n roots. Okay. And its value is in this. Okay. Now, also we have seen they are in the form of a geometric progression. So these roots are in the form of a geometric progression. We will to show this. Okay. Now, so we find the first root z not equal to 1. So this is the first root here z not equal to 1. Now we denote the second root for omega. Let z1 equal to omega. And third root z2 equal to omega square. And fourth root z3 equal to omega cube, and in this way and so on, last zn minus 1 equal to omega raised to n minus 1. So these are the roots of z raised to n minus 1 equal to 0. Now therefore the roots of unity z raised to n minus 1 is equal to 0 are 1 omega square omega cube dash omega raised to n minus 1. Okay. Now we have seen that the common ratio, the two consecutive terms. So 1 and omega, the common ratio is omega upon 1 is omega. Next two terms, omega square upon omega is omega. Next two terms, omega cube upon omega square is omega. And in this way, the common ratio is same. And this shows that these roots are these roots of unity are in the form of a geometric progression. Okay, hence the proof. Now, also their sum is equal to 0. So we have to show that their sum is equal to 0. Now, also their sum is equal to 0. So that is 1 plus omega square plus omega 2 plus dash omega raised to n minus 1. So this is the sum of a geometric progression. Now we know that the formula for sum of a geometric progression is a into bracket 1 minus common ratio raised to n divided by 1 minus common ratio. And here first term is 1 and common ratio is omega, and therefore is equal to their sum is equal to the first term is 1 into bracket 1 minus common ratio r is omega, so omega raised to n divided by 1 minus omega. So the sum of a geometric progression is 1 into 1 minus omega raised to n upon 1 minus omega, where omega is common ratio. Now the omega is root of a equation z raised to n minus 1 equal to 0, and therefore this root satisfies this equation, and hence omega raised to n minus 1 equal to 0, and therefore omega raised to n equal to 1. And now we put this value in this equation, and therefore the sum of a geometric progression is 1 plus omega square plus omega cube plus dash dash omega raised to n minus 1 is equal to 1 into bracket 1 minus omega raised to n. So value of omega raised to n is 1. So 1 minus 1 is 0. And therefore 0 upon 1 minus omega, and therefore its value is equal to 0. And this shows that their sum 1 plus omega square plus omega 2 plus dash dash plus omega raised to n minus 1 is equal to 0. And hence the sum of a geometric, the roots of a geometric progression is equal to 0. So hence the proof. Okay. Now the next, the examples on the application nth roots of unity. Now we take first example, example 1, find all the fifth roots of unity. So the above formula is nth roots of unity. So where n is a any integer. So first, in first example, so we take the n equal to 5. Now we have to find all the fifth roots of unity. Now solution is given n equal to 5. Okay, and therefore the equation is z raised to 5 equal to 1. That is z raised to 5 minus 1 equal to 0. And therefore the z has a 5 roots. So we have to we know we have to find the 5 roots of a complex number z. Now we know that the formula of nth roots of unity we have seen in the above question. And therefore the formula is the nth roots of unity formula is zk is equal to the cos of 2k pi upon n plus I sin 2k pi upon n, equation 1, where k equal to the 0, 1, 2, 3, 4, 5 dash dash n minus 1. Now in this example we have to given the values of n. So n equal to 5. Now we put this value in the equation 1, and therefore the equation 1 becomes from 1. So zk equal to the cos of 2k pi upon n equal to 5. So 5 plus I sin 2k pi upon 5. So equation 2. And the value of k we put here 5, 5 minus 1, 4. So the value of k up to the 4, and therefore k equal to the 0, 1, 2, 3, 4. Okay. Now we find the each root of the complex number z. Now we put k equal to 0 in equation 2, k equal to 1 in equation 2, k equal to 2 in equation 2, and k equal to 3 equation 2, and k equal to 4 in equation 2. So these are the 5 roots. Now we find one by one in the following. Okay. Now from we put k equal to 0 from equation 2 we have now z naught equal to the cos of 2 pi into 0 upon 5 plus I sin 2 pi into 0 upon 5. So this is the value 0. So cos 0 plus I sin 0, and we know that the cos of 0 is 1 and sine of 0 is 0. So 1 plus 1 0 is equal to 1. So first root is z naught equal to 1. Now we put k equal to 1 in equation 2. Now from 2 we have z1 equal to the cos of 2 pi into 1 upon 5 plus I sin 2 pi into 1 upon 5, and therefore z1 equal to the cos of 2 pi upon 5 plus I sin 2 pi upon 5. So this is the second root of a complex number. Now for k equal to from equation 2, so we put k equal to in equation 2. So z2 equal to the cos of 2 pi into 2 upon 5 plus I sin 2 pi into 2 upon 5. Now the root z2 equal to the cos of 4 pi upon 5 plus I sin 4 pi upon 5. So this is the third root. Now we put k equal to 3 in equation 2, and therefore from equation 2 is equal to cos of 2 pi into 3 upon 5 plus I sin 2 pi into 3 upon 5, and therefore z3 equal to the cos of 6 pi upon 5 plus I sine 6 pi upon 5. Now this is the fourth roots of given equation. Now we put k equal to 4 in equation 2. Now we have, so this is 4, and therefore z4 equal to the cos of 2 pi into 4 upon 5 plus I sine of 2 pi upon 4, into 4 upon 5, and therefore z4 equal to the cos of 8 pi upon 5 plus I sine 8 pi upon 5. This is the fifth roots of a complex number, and therefore the nth roots of complex numbers are z0 equal to 1, z1 equal to cos of 2 pi upon 5 plus I sine 2 pi upon 5. Now z2 equal to the cos of 4 pi upon 5 plus I sine 4 pi upon 5. z3 equal to the cos of 6 pi upon 5 plus I sine 6 pi upon 5. And last z4 equal to the cos of 8 pi upon 5 plus I sine 8 pi upon 5. Now these are the five distinct fifth roots of unity. Okay. Now the remaining parts will be continued to the next lecture. Okay. Thank you.